Okay, we're going to move on. Who was not here last time? You're good. Okay, let us move on. Last time we finished differentiation, we're going to move on to section 1.2, which is integration. And then we will move on to chapter 2, which is differential equations. So technically, homework 1 covers sections 1.1 and 1.2.
So then 23 through 37, is it okay if we really struggle with them?
Yeah, especially the ones.
No, it's not okay to struggle with anything.
I'm doing my goal.
Anyway, you still have another few days to work on that. So 1.1, 1.2, that will be due on Monday as homework 1.
I was panicking right now before this class. I was like, trying my hardest.
That's good. That's good.
We should get heads up next time. Like, hey guys,
So textbook is in the math department. Okay. But if you can't get it, chapters 1, 2, and 3 are on the math department's website. The PDF, so you can just do the homework from there.
All right, settle down.
2 or 5 hours in the back.
Let's remind ourselves how to do integration. The basic rules. Everything comes down to knowing the basic rules. This is where it begins. There's a power rule for integrals. Integral of x to the n dx is equal to
n plus 1 divided by n plus 1 plus c.
c. Forget that c, I'm going to punish you for it. I'll take off the point. This works for n not equal to minus 1, clear, because you'll divide by 0 there. What if n equals minus 1? Then what happens? What's the integral of x to the minus 1? Right, that's just 1 over x dx, which you should know by now is ln x in absolute values plus c. Right? So this is a very important rule here. And this integral of 1 over x dx equals ln x plus c is another very important rule. These you should have memorized. Examples. Do those examples. Integral of x cubed dx.
X to the 4 divided by 4.
Right. Direct application of that rule. Nothing fancy here. X to the 4th over 4 plus c. Okay. A little bit harder, more advanced. How is this?
X to the 5th.
20x. Oh no, sorry, never mind. I started taking the derivative of that.
X to the 5th. Plus 3 4 plus x.
Right, so technically there's a 5 in front here, but then you divide by 5 and that cancels. So you get that x to the 5th plus
3x to the 4.
3x to the 4th over 4. Add 1 to the power, divide by the new power. This one.
7x squared over 2.
7x squared over 2.
Plus s.
Integral of 1 is x plus c. Good. This one.
Is that the copy?
Come in. What?
Foil the top.
Foil the top.
Yeah.
Okay, so we have x squared plus 5x plus 6 over x squared.
Divide each by x squared.
Yep. Okay. Remember here, you can't just integrate the top and integrate the bottom and stick them together. In fact, you get 0 for the problem if you do something like that, because that's crazy. There's no rule. Notice in the rule, there's no division here. Right? You can only apply it when it looks exactly like the rule. So you divide this into each. So you have x squared over x squared, 1 plus 5x over x squared plus 6 over x squared dx, which I can simplify. So x squared over x squared. So this is 1 plus 5 over x plus 6 over x squared dx.
How did you? Oh, I got it.
Okay, let's start integrating these guys. Integral of 1, x plus integral of
5 ln
5 ln x. Then the integral of 6 over x squared. Oh, that's just 6 ln x squared, right?
No.
No. Because you get a 0 for doing that. Good. Okay, how do I actually integrate 6 over x squared?
Is it 3 ln x squared?
6 x to the negative 3 over.
Negative 6x to the
So if I have 6 over x squared, how do I think of that?
you can
6x to the minus 2. Now I apply the rule. If I add 1 to the power, what do I get? Minus 1, right? And then I divide by minus 1. So this becomes minus 6 over x.
Can we just leave it as x to the negative 1?
It's exactly the same thing. Questions so far?
Yeah, for sure. I
Yeah.
got lost from that. This is a continuation of,
Oh, over there, yes.
so from that last step to this is.
Okay, tell me where did I lose you? Are you lost with the x?
So, each term.
Okay, can someone explain why is this an x?
Are we taking the derivative of?
1, which is x.
Because
The integral of 1 is x.
Integral of 1 is x, why?
Because you can think of 1x to 0, and then you add 1, so it's x to the 1.
Right, so there's a tacit rule here that the integral of a constant dx is just a constant times x. And kx plus c. So the reason is for any constant, you can think of it as kx to the 0, and then you add 1 to the power divided by the new power. Right, so if you have the integral of 1 dx, you think of this as the integral of 1 times x to the 0 dx. You add 1 to the power, you get x to the 1, divided by the new power. That's where the x comes from. In general, the derivative of a constant is the constant times x, if you're doing dx. Right, so that's, you can memorize that rule if you want, but it's just an application of the power rule. Right? So the integral of 1 gives us x. Moving on to here was the second rule that I gave you, right? Because this. So that explains the 1. If you look at the second term, that's the 5 over x. The thing is, with integrals, we can factor out constants, so I can take that 5 and put it out in front. I do that with 1 over x. This guy, I have the rule for. That tells me that that becomes ln x. And then this 5 just ends up. So, hence this term. Now, when I move on to the 6 over x squared, again, there's no rule, as you can see before, that where I had this division with a square in the bottom. So the trick was to rewrite this using algebra, we know 1 over just means a negative power. And then I just applied that same rule that we had. So it's -1 plus 1 over -2 plus 1. Add 1 to the power, divide by the new power, and you end up with this. So that's term by term, you just do it. So the integral of 1 was x, integral of 5 over x was this, integral of 6 over x squared is this, by applying the power rule.
So we take the integral or the antiderivative of each term.
Of each term separately, yes, and that would be it.
Backwards.
Would it be wrong to rewrite 6 over x, 3 ln of 1 over x squared? Sorry, 3 ln x squared.
Yes, that's totally wrong.
It wouldn't be the same.
Two totally different functions. And that's also sort of a blasphemy. That's what I mentioned in the syllabus. That's the rule number 1 right here is the rule you'd be breaking. So you look in the syllabus on rule number 1 in that section. So yeah, the things like 6 over x, if you even look at the graph for that, that looks like this. Or if you look at something like ln x, that graph looks like this. They're completely different functions. They're not the same at all. Right? This guy doesn't even exist over here. Right? They're completely different functions. Okay. Another basic rule. Integral of e to the x dx.
E to the x
Plus
Integral of e to the x.
plus c.
It's the same. Well, c. It's important. Okay. That's another thing you should memorize. Those are pretty much all the basic rules that you will need for this course. I mean, an example of that. That is its own example. We can change things a little bit, which, before we do that, I want to tell you about the other technique. So basically in 205, there's like one integration technique beyond the basic rules that you guys learned. This was substitution.
I have a question about e to the x.
Yes,
There's some problems with like e to the kx.
we're going to do that now after substitution. Because where that formula comes from, they actually applied substitution. So I figured I'd tell you what substitution is first, and then I deal with that case. But yeah, in general, I guess we'll come back to this. E to the kx dx is equal to 1 over k e to the kx.
Oh, that's what I'm supposed to do.
Right? Where k is not equal to 0. Right? But where this formula comes from is substitution, so I'm going to tell you about substitution. Okay. So in general, this is used to integrate composite functions. Right? Means functions plugged into other functions. But you don't even need to think of it that way in this course, because it's the only other technique above a basic rule that we will do. So basically, in this class, use it to transform something. That does not look like a basic rule. Into a basic one. Right? So pretty much anything that looks scary, odds are it's like a substitution, if you don't simplify it first. So just do an example of what I mean. slightly a review, so I won't go into too much of the theory. Let's say I had something like x times the radical of x squared plus 4. So now there's a lot going on here. One, I have a product of functions, right? I have something, an x times this radical function, right? So it already doesn't look like any basic rule I have. There's no rule that I had that had two functions multiplying each other, right? Second of all, there's nothing that told me how to deal with a huge radical with all sorts of stuff underneath it. So this looks kind of complicated, looks scary, right? Basically, substitution is going to be the technique that we use to make it into something that's not scary. So here, this is scary. No basic rule applies. Right? Because it doesn't look like an x to the n, it doesn't look like a 1 over x, and it doesn't look like an e to the x. Right? It looks like none of these guys, which are all the rules we have so far. So, strategy is to use a substitution. How does this work? Substitute an expression in the integrand for u, right? With two qualifications. So I'm going to make a substitution. I'm going to replace an entire expression in this integral with the variable u. And there are two rules for how I choose my u. One, the substitution must make the function simpler. Two, the derivative of this substitution substitute to the expression must be a factor somewhere else in the integral. Those are the two rules I'm going to use to make a substitution. Parenthetical statement, if we're off by a constant factor, in 2, doesn't matter. We can factor constants out. So I'm not worried about the constant multiplier in front, I'm worried about the function part. Okay, so let's see what this would look like for this integral. Okay. So let's start with rule 1. Substitution must make the expression simpler. So I look at this. What makes this complicated? The radical, right? If it was just an x, no problem. Power rule, right? Radical of x squared plus 4. That's what makes things complicated, right? Now, what if it was just a radical of x? Would that be fine?
You change it to.
Yes, you could change it to x to the 1/2, still apply the power rule.
Yeah.
So it's not necessarily the radical that makes it complicated. What's the thing that makes it complicated? The thing under the radical, right? So the first thing I do, I look at this thing, it looks crazy. I'm going to identify what actually makes it crazy, right? That x squared plus 4 makes it crazy. So what I'm going to do, u equals x squared plus 4, right? I'm going to substitute something that's going to simplify this expression. If this was just a single variable, it would be easy. It would just be x times x to the half, combine it, use power, right? What makes it complicated is the x squared plus 4. So I'm going to say u equals x squared plus 4. Okay, so that's the first thing. The second thing I have to check, is the derivative present somewhere else as a factor? Well, let's actually do it. The derivative of u would be what? 2x dx, right? Right? What I really did was du dx, and then I multiplied the x on it. Right? So now I look, remember, I don't care about the constant factor. So this 2, essentially I'm not worried about it if there's no 2 there. What's important is there an x there? And I look at it, oh, there's an x right here. Look at that, right? So the x is there, that's good, right? So what I can do is, from here there's a couple ways you can proceed. The way I like to do it is to try to solve for what I have there. So I see that I have an x there. The 2 is messing up, so I can divide both sides by 2. Okay. That's one way you can do it. Make a note here. I'll show you a different way to proceed after I complete this method. Huh?
Oh, I was doing it,
Are
sorry.
you talking to yourself? Okay, only math people do that, don't we? Anyway, okay, so here's the thing. This is what I have in my original integral. Notice here, I do have an x dx, right? See that? I have that x dx. Now I get the fact that x dx is actually equal to 1/2 du, which means if I write 1/2 du, I can sort of replace this with that, right? I'm just going to go through this integral and start substituting things, right? So, got x radical x squared plus 4 dx. That's actually equivalent to the following, right? If I write 1/2 du, that guy is going to replace this x dx, right? X dx will become 1/2 du. Right? What do I have left over? Well, this radical of x squared plus 4. But what is my x squared plus 4? U. That's just a u. So that guy is going to come over here. He is just going to be a u. The radical is still there. You probably need different colored chalk for this. But basically, what this becomes, as you will see, is now my original integral becomes 1/2 the integral of radical u du. Right? I swapped out the x dx, that becomes 1/2 du, that's 1/2 du. And then my x squared plus 4 is just a u, so I put that where the x squared plus 4 was. Now what about this integral? Can I do this one?
Yeah.
It looks like a basic rule now, right? This is just 1/2 times the integral of u to the 1/2, right? Which is something I can apply the power rule to, right? So I went from something that looks insanely complicated, relatively speaking, to something where a basic rule applies, and I do this using substitution. So what will be the answer here? U to the 3/2 divided by 3/2 plus c. How do I divide by 3/2? It's multiplying by 2/3, right? So I multiply by 2/3 u to the 3/2 plus c. 2 should cancel, because you can cancel across multiplication. I end up with 1/3 u to the 3/2 plus c. Are we done? Right, so someone asked me a question with x, I can't give them an answer in u. All I do now is just replace this u with what it was originally. This is called back substitution. So ultimately this would be equal to 1/3. My u was actually x squared plus 4 to the 3/2 plus c. And that ends up being the answer. Let's do another example. E to the 5x dx. How do you proceed? Well, if it's just an e to the x, I know how to deal with it, right? What messes it up is the power is now 5x, right? So what I would do is u equals that 5x, right? My du would be 5 dx. Now remember, constants I don't really care about. I can divide by it. So what I'm going to do now is just I'm going to replace the dx with 1/5 du. So this guy becomes 1/5 du. Will replace my dx. So when I write that, that's substituting this guy. And what do I have left over? Well, I have that e to the 5x, but 5x is u. So this is just e to the u. In other words, I have 1/5 integral of e to the u du. And that looks like a basic rule. There's no constant here. No coefficient other than 1. What's the integral of e to the u du? Just e to the u by our rule. And u was 5x. Okay. Let's get a little bit abstract here. E to the kx dx. What do I do to figure out what that integral is? Walk me through it. How would I know that? U equals kx. Remember that k is a constant. My du would be k dx, which means 1 over k du is equal to dx. So this integral becomes 1 over k du replaces my dx, and I'm left with e to the u. Applying the basic rule, I just get 1 over k e to the u. And now I replace the u with what it was originally, kx. Hence I get this new formula, e to the kx dx is equal to 1 over k e to the kx plus c. This of course assumes that k is not 0, because you can't divide by k. Right? What if k is 0? Then e to the 0 would just be 1 by the power rule. Right? So that would just be x, right? So as long as your k is non-zero, this is be the formula. So basically what that helps you now is it sort of saves you some time. You don't have to go through a substitution every time you see something like e to the 5x. We can do all those integrals pretty easy right now. About e to the minus 2x dx, or e to the pi x dx. Or e to the 1/3 x dx. Or e to the x over 2 dx. The idea is I can now consider this formula as one of my basic rules. It also works fine with the original rule, right? If my k is 1, I get e to the x, and then I just get e to the x plus c. So if you're going to memorize an exponential rule, this would be the better one to memorize, because it deals with a more broader array of cases. So right now, with this rule, I don't even need substitution anymore. It happens all in the background. What's this integral? What's this integral? What's this integral?
3 e to the 1/3 x.
What's this integral?
2x.
Questions? You guys finished already?
What if it's x to the power? We try to do it the long way, right?
X to what?
To the power. Like, it's not 1 to the 2 to the 3 to the...
Oh, don't worry about those cases. Most of them would be impossible. For example, like e to the x squared has no antiderivative. Really. Right, there are some integrations that are possible. There is no function that when you differentiate it, you get that.
So expansion of power, expansion of
Yeah, so right. The only way that could work
It has x in
is if I put an x in the front. Alright. Which, hey, we should probably do that example.
yeah.
So yeah, next example, right? It's just e to the x squared, impossible. However, throw an x here, and things become very possible. How?
U is equal to x squared.
Right, so again, weird sort of function, there's a product of an x and an exponential, and then there's a quadratic in the exponential, don't know. Then you go back to substitution, right? If it's not one of the basics rule, it's substitution. That's the class right? If we're in 202, things would be a lot more spicy. But in 209, substitution is the only thing exotic integration rule you need to know. So basically, if it looks ugly, it can either be you have to simplify first, like that problem I gave over here where we just foiled out and just canceled stuff. If that doesn't work, which it won't work here, it's a substitution. So then we think, what makes this complicated? Well, the x squared makes it complicated. Is that a good substitution? I don't know. Find the derivative. Oh, here's an x. Here's an x. It's a good substitution. So it means I can replace x dx with 1/2 du. And then my e to the x squared becomes e to the u, because my u is x squared. So this becomes 1/2 e to the u plus c, and my u is actually x squared. If you differentiate this, you get that. So that would be the answer. Let's do a couple more.
I would have a quiz today.
No? Are you still worried about that?
Surprise people.
When do I ever surprise it?
That last
Last time.
No. Bassett asked for the quiz. I mean, it's even. He literally asked for the quiz. I heard
Then
him.
you criticized him. You were like a quiz on the first day.
Thank you.
What
And so
does
we were
that?
like, this guy's cool, and then you were like, pull out the quiz, surprise, surprise.
No, I give the people what they want. Okay. He asked for a quiz. So I gave you
Should have
guys a
given
quiz.
just
Like,
a quiz.
But he asked for it.
Yeah, not everyone else.
no, we're all in this together. We're a family. Okay. Ride or die. We win together. Come on. You can't just send him alone to death. Come on. Jeez. He's our brother. Crying out loud.
Not mine.
Try that. Okay. See this integral on a test, what do you do?
Do something.
Give up.
You take out the 5, so it's just 5 integral. No, you don't do that.
Yeah, you do.
You could do
Yeah,
that.
you could do that.
You could.
You
I'm
could.
gonna take my wrong advice and then on test
Is it
you guys.
5?
Well, can you make, you.
You find that u is equal
Ah,
to
so you say u equals ln x, right? Because obviously the denominator is what makes this complicated.
Yeah.
Right? Okay, so u equals ln x, my du would be
1 over ln.
1 over x dx, right? Do I have a 1 over x dx? Sure, he's right here, hiding. The x is in the bottom.
Yeah.
Right? So let's say you weren't sure that's what. The whole denominator looks complicated, so maybe you thought u equals x ln x would have been the thing to do. What would have happened then? You did du, what would you get?
You
You
get
have to do the product rule, what would you get?
X 1 over X.
X times 1 over x
which is
Plus ln x.
plus ln x, all of that dx, right?
Yep.
So you'd end up with 1 plus ln x dx, right? And then you look, is this over there? No, right? So then you're like, that's not the right one, right? And then you might have tried something else, right? But usually when you see an ln x and there's an x, that's going to be the guy you want to do. But I just want to show you that the two rules that I gave you earlier, those are the things you always think about. What makes it complicated, once you figure that out, the derivative must be somewhere else in the function. This expression didn't show up anywhere else, so this would be the wrong substitution to use. This substitution is okay because it shows up elsewhere. So now what happens?
So it's 5 integral of 1 over u du.
1 over, the x dx gets taken away by the du, that replaces the x dx. So what I'm left with here, the 5, he pulled it out, that's fine. My ln x is the u, so it's just 1 over u. That looks like a basic rule. What's the integral of 1 over u? Is ln of the absolute value of u, plus c.
So then it's 5
5
ln the absolute value of ln x
ln x.
plus c. Oh, we
Right.
would have put absolute value inside the absolute value.
No.
It can't be like double.
No, u wasn't, there was no absolute value. Yeah, you can plug in ln into an ln, that's not illegal. So that would be the final answer.
Do we always have to write the absolute?
Yes. Because if you did 205, you would have learned that you can't plug a negative into an ln. The absolute value is to always keep it positive, and so things work out nicely. There's a whole discussion that goes into it.
Good to know.
But basically, yeah, the rule has absolute values into it. Always put the absolute values. If this number were something that was always positive, like u was x squared plus 1, technically you don't need the absolute values, but it wouldn't be wrong to put it anyway, so always put absolute values. Okay. See, this on a test, what do you do?
You
Panic. Pray. Yeah.
You let your u be x to the 4th minus 7?
Okay. So you look at this and, oh, that looks complicated, it doesn't look like a basic rule. What makes it complicated? Well, dividing by a quartic polynomial doesn't make things any nicer. So then I might think, okay, u equals x to the 4th minus 7. Why didn't I pick the top?
Because we need to do the derivative x to the 4th.
Because when I take the derivative of an x cubed, I get an x squared, which doesn't help me get rid of this guy. So it wouldn't make things simpler. The derivative wouldn't be there, right? However, if I take the u to be the x to the 4th, then I take the derivative, that's going to give me the x cubed, right? Which is good. Now this has a 4x cubed, that has a 3, doesn't matter. Constants, we can factor them out. So I can just divide both sides by 4. And then just replace things one by one, we run out of space. So what does this become? So there's this 3 here, I can pull that out, so he's just hanging out here. Then I have 1 over 4, so that's 3 over 4 du. Now when I write 3 over 4 du, it replaces the x cubed dx, so that's gone. So the only thing I have to worry about now is the bottom. So it's just 1 over u. That's a basic rule. That gives us what? ln of u. And then I replace my u with what it was in the beginning. Okay, so what do we substitute here?
It's a horrible looking equation. I wouldn't substitute that way.
Yeah?
Can you split it up?
We could split it up, sure.
Just combine the x with the radical x.
And get what?
X to the 3 over 2.
Can we integrate each one separately?
You can. Okay, then what?
Power rule.
And then power.
Power rule, right? There was no such trick question. Okay. So someone mentioned that can't we just split it up? You could. Basically what that would involve is you writing this out. Which does nothing to help you solve the problem. It's literally just an extra line that you'd write just because. If you just know in your mind that I'm just going to do this, then that separately, there's no reason to actually write this out. I mean, you can do it if you want, but you're wasting time essentially. I'm thinking about this one at a time anyway, so I don't need to express it that way. So I just worry about this guy first. What's the integral?
3x to the 5 over 2.
Over 5 over 2.
Over 5 over 2, which is the same as multiplying by 2/5 plus x to the 4th over 4 minus 2x. So this is 6 over 5 x to the 5 over 2 plus x to the 4 over 4 minus 2x plus c. So that looks scary, but it was really a basic rule in disguise. You didn't need a substitution. What this guy?
Take u equals 4x to the 3rd minus 3x.
Yeah, definitely the power in the exponential makes things crazy. That's just wrong. That's unnatural, right? So u equals 4x cubed minus 3x dx. So my d would be what?
12x to the 3rd minus 3. Yeah.
Uh-oh.
Take 3.
Then take 3 out. Jeez. Oh, thanks for killing my thought. I want to be dramatic. Oh my god, what are we doing? You just like said it so anti-climactic. Oh, you just take the 3 out. Like, oh my god, oh, there's a 12. And, oh my god, what do we do? It's not elsewhere in the. Yeah, it was a constant factor of 3 that was out. Just move that 3 over. 1/3 du would give you that 4x squared minus 1 dx. And so now you start to replace everything. So I write 1/3 du, and that replaces this whole monstrosity. I'm left with e. I didn't do anything with that, but the power, I made it u. Integral of e to the u is e to the u. And so this is 1/3 e to the, I replace it with that. 4x cubed minus 3x. Okay. So that ends our review of 205. That's basically all you need to know. How to differentiate things, how to integrate things. The idea is you know the basic rules and you apply them. Anything that doesn't look like a basic rule and you can't simplify it to make it look like a basic rule like we did here, substitution is the guide. figure out what makes it complicated, let that be a u. Double check that when you differentiate that thing, you get something else in the function, and then you're good. After that, it's a basic rule.
What chapter did you say this was?
We're still all in chapter 1. We just finished chapter 1, which now homework 1 is due next class. So, we're going to move on to chapter 2. Yes. Yeah.
How do you want to write the 1 plus x over plus 2?
Integrate 1 plus x over. Oh, that's a hard one. Does anyone know? Huh?
It said you have to divide separate. You can do like 1 over x plus 2 plus x over x plus 2.
Okay. And then what?
So,
Yeah.
like if you, what she said, if you separate it, so it would be like x, parentheses x plus 2 to the -1 times x plus 2 to the -1.
Yeah, that wouldn't really help though. You need more manipulation. You can make a different manipulation to begin. Yeah? Long division would be one way to do it. So if you want to simplify this, one is you actually do long division, which you may or may not remember, but it would basically look something like x plus 2 divided into x plus 1. X into x goes 1. 1 times x, 1 times 2 is 2. You subtract this line from the line above, x's die. 1 minus 2 gives me -1. X cannot go into 1, so that's my remainder. So what this ends up being is 1 minus 1 over x plus 2. In which case, that becomes x minus ln of x plus 2. Where technically this is a substitution. Come again? You didn't have to. There are several ways to do it. Long division would be the way that it's more writing, but it's more straightforward to think of it that way. Another way that when you see things like this, when you see the degree in the top, especially, it can work in other cases, but you won't get anything more complicated than this, is the same as the degree in the bottom, right? Notice that the top is a first degree polynomial, the bottom is also a first degree polynomial. We can do this with, the trick is to put the denominator in the numerator. I'm going to explain what I mean by that. So you see this guy here, I have a 1 plus x over x plus 2. What I'm going to want to do is put the denominator in the numerator. Essentially, what that means is I want to see an x plus 2 in the top. Right? The reason for this will become clear momentarily. How do I get an x plus 2 in the top? Let me just, no, just how about add a 2, right? That gives me an x plus 2. Can I just add a 2?
That violates a rule I learned.
Exactly, that would violate a rule. How do I fix it?
Add 2 in the bottom.
No, that would not be the same. Subtract the 2, right? Let's add a 2 and subtract a 2. So I'm really adding 0. I literally didn't change anything, right? Why did I do that? Oh, jeez, Jhevon, I really got you. Let's see. This x plus 2, let's leave him here. X plus 2, right? That's that guy. What is 1 minus 2?
-1.
-1 gets left over. Do you see what to do now? how you divide into each.
Yeah.
If I take an x plus 2, divide into x plus 2,
Two more.
and then I take an x plus 2, divide into that. Right. Basically, this becomes x plus 2 over x plus 2 minus 1 over x plus 2. Which is basically 1 minus 1 over x plus 2. Now, normally I jump from here to here, but so then you can integrate that and it becomes that. You get the same answer. That one was just for fun, though. I don't think you get things like that in this course, really.
Well, it was on the
But I mean, chapter 1, we go through chapter 1 because it helps you out with chapters 2, 3, yeah, it helps you out with a bunch of other chapters. But the application in the other chapters would never require an integral like this. At least you won't get any problems that require it. Learn how to do that. You can, do it at parties, with other kids. But I wouldn't worry too much about it for the rest of the course. Let's move on to chapter 2. Two is a topic we call differential equations. How differential equations is dealt with in this book is very underwhelming. These guys are more important than you can possibly imagine. Differential equations are one of those areas in math that it's highly applicable to your real life. It's very application intensive. There are so many things that we can describe in nature that follow differential equations, and we will actually do them. But let's actually look at the ones we'll be doing. Tell you what it is first. A differential equation is an equation with derivatives. That's basically it. So example, y prime equals y, or y double prime plus 2y prime minus 3y equals 0. Or x squared y double prime minus 2xy equals 4. Right? Basically you have a regular equation, but there are derivatives hanging out, like they're normal variables. Right? We call these guys differential equations. Just equations with derivatives in. It turns out there are many processes that can be described in terms of differential equations. Bacteria growth, radioactive decay, compound interest. Right? A lot of those guys, we can have equations of this form that will tell us what they're doing. Right? So the number e comes from solving a differential equation. ln you can get from a differential equation, all of that. So these guys are really important, very applicable. But that's what they are, right? I don't want to tell you anything else about it. So this is technically called an ordinary differential equation. I don't want to make it too complicated. So for our purposes, that's a differential equation. It's not the exact definition, but we'll move on. do some examples. Let's look at this differential equation. Let's say I told you dy dx is actually equal to x squared plus 1. This is a differential equation. Why? There's a dy dx in it. So it means I already took the derivative of something and I got x squared plus 1. This is going to sound way more complicated than it actually is, but I'm going to write it down anyway. To solve the differential equation, we need to find another equation without derivatives. That's the important part. I don't want to have dy dx. I only want x's and y's, basically. That is true exactly when the differential equation is true. So the goal is here to figure out what equation must be true for this to be true in terms of x and y. One trick that you might realize here is we can treat dy dx like a fraction. It's a little weird, won't get into the theory, but basically we can treat dy dx as a fraction. So anything we can do with a fraction, we can sort of do with dy dx. So let's start by working on this one. Try to solve the above differential equation. Any ideas how to go about this?
But what is that? Can you read that? To solve a differential equation?
To solve a differential equation, you need to find an equation without derivatives, meaning I just want an equation with x's and y's, no derivatives in it, right? That's true whenever this is true.
Multiply.
What?
And it's true exactly where the differential equation is true.
Is true, yes. So let's start with this. Dy dx equals x squared plus 1. What equation must be true for the derivative to be x squared plus 1? You can sort of take the integral, right? Note, if my y was equal to x cubed over 3 plus x plus some constant, then what would dy dx be? Well, differentiate this, right? Differentiate derivative of x cubed over 3, it's actually x squared. Derivative of x is a plus 1. Derivative of a constant is 0, right? So here's an equation that is true when the differential equation is true. And there are no derivatives here. I only have x's and y's. So it's like a normal function to me, right? So this is some y equals f of x that's true when my differential equation is true. Sort of did that fast. Let's sort of see how we can build up to this function. So the trick is the following. Remember I said this guy we can sort of treat like a fraction, right? So I could do something like multiply both sides by dx. So I multiply this by dx, what happens? The dx is cancelled. I'm just left with dy equals x squared plus 1 dx. Now something like this should start to look familiar to you, but there's something missing, right? The integral. If there was an integral sign here, yeah, I know how to deal with that. So let's what? It's an equation. Let's integrate both sides. right? So there's like a 1 here. Right? Now if I integrate 1 dy, what do I get?
Y.
Plus y. Power rule. Integrate x squared plus 1, again I apply the power rule. I get that x cubed over 3 plus the x plus a constant. Right? Technically there's a constant here, but I just move it over and all the constants I concentrate on the right side. So that's how I get the equation. I sort of break up the dy dx, trying to get an integral in there, integrate both sides, right? To get from a derivative to a normal equation without derivatives, you're going to have to integrate at some point. That's basically the idea. So if I want to get rid of a first derivative, I'm going to have to integrate once. If I want to get rid of a second derivative, I'm somehow going to have to integrate twice, and etc. Okay. Let's do another example, and then I'll sort of talk more about this. dy dx equals 2y. What function must be true for that to happen? Right? If I say y equals f of x, what kind of function would actually solve this? Where if I take its derivative, it becomes 2 times the original function.
You just solve that, right?
How would you do that?
I'm moving 2 to the other side.
Okay, let's multiply by dx, right? It worked last time. Let's actually do it. Now what?
Now you move the y to the, no.
Right, you see a y and a dx, they don't really match up, right?
So move the y.
So you know what? Maybe get rid of that y. Let's move that y over. What does it become? You have to divide by y. So what does it happen over here?
Dy.
Dy over y. Or like 1 over y dy, same thing. Here's 2 dx. Now this looks normal. I can integrate this side and integrate that side. There are only y's on this side, dy. Yeah, what's the integral of 1 over y dy? ln of y.
Is it blasphemy to cancel out the y's? Like in the second equation, so 1 over y dy, can I
Just a D.
Yes, you can. dy is one thing by itself. It's not like a d times a y. It's dy is like a
variable
unit.
in and of itself?
Yeah, it's like Riemann sums from 201. That represents the delta y. It's not the actual y.
It would make it something.
So integral of 2? 2x plus c. Right? So now, let's say I don't, technically this is an answer. You could have written that as an answer. But let's say I want to write the answer as y equals f of x. A lot of times I want that.
Can you do the e on both sides?
Right, I can raise both sides to the e, right? So now if ln y is equal to 2x plus c, what I do is throw this side in e and throw that side in e, right? Now if I take e to the ln of y, what happens? Get the y. Then I'll have e to the 2x plus c, right? Here, at this point, it's a lot nicer to write it this way, like c e to the 2x. Why was that valid? Does it help to say that this is a different c from that c?
Because even the C is the number constant.
Okay, but how do I go from e to the c, this to e to the c?
Because equal x plus C is.
Right, this is e to the 2x times e to the c, rules of exponents. Now e to the c is just a constant, so that's that guy, right?
Just leave it like that?
So then y is equal to c e to the 2x, right? This would be my solution, right? And you can check this. If you differentiate this, what do you get? It's 2 times that function, right? Here my dy would be 2 times y, right? Because your derivative of e to the 2x is just 2 times that thing, right? So this is actually a function. If this is true, that has to be true, right? And vice versa, right? What else do I want to do?
Can we move it like a d to the 2x plus c?
Yeah. Can we do that?
There's a reason why I wouldn't want you to do that. It wouldn't be wrong, but The reason is going to be clear soon. Well, you just want to put that c in the power as a constant multiplier. Suppose we are given, and it's a so-called initial condition. I.e., the value of the function at a certain point. I'm going to sort of generalize this method soon, but I just want to work through a couple of examples so you guys sort of get a feel for it. So example, suppose I tell you, I'm looking for a function where its derivative is 2 times itself, and I know, for example, that when my x is 0, my y is 5. Can you find such a function? Well, we'd have done everything that we did there, right? So we went through that whole process, right? And we end up with y equals c e to the 2x, right? Now what? Plug in the values we're given. Notice here, I'm saying my x value is 0. And then the y value is 5 at that point. So what can I say here? Since y of 0 equals 5, this means when my x is 0, c e to the 2 times 0, the output value is 5. Right? So then what can I say? So I have 5 equals c times 1. In other words, my c must be equal to 5. Therefore, my y function would be what? 5 e to the 2x. Okay. Why would something like this be important? Right? First, notice what this equation is saying. The rate of change of y with respect to x is 2 times the current value of y. Right? That could be, for example, you know what? I brought these hamsters from, from this pet store. They have sex like rabbits. You know what? Every week they double. Like, I bought 5 hamsters last week. Now I have 10. The following week I'll have 20. The following week I'll have 40. Right? They reproduce like rabbits. Right? Every time the rate of change of this population is doubling whatever its original value was at some other point. Right? Right? So now you're hearing that from your friend, you're like, holy crap, I actually bought 5 hamsters yesterday. Right? So now I'm like, okay, I have 5 of these hamsters. They're going to be doubling every week. How many hamsters will I have in a month from now? Right? For example, you might want to figure that out. Right? How would you figure that out? Well, you'd start by this differential equation. You'd say, well, the rate of change of this population, it's doubling in size every week. How do I know what the population will be? Well, I solve this differential equation, and now I get this. This is the population size. This was the number of the population. So now this equation would describe how this population is behaving. And so now I can say, well, how many rabbits will I have in a month time? Well, if x is the time in weeks, then I would just plug in, say, 4 here. Right? So I have 5 times e to the 8 rabbits, or what do we have, hamsters, right? What's 5 times e to the 8? You guys are supposed to have rabbits. Because that would be nice. Let's say, what is y when x equals 4?
14,904. Yeah.
14,000?
Yeah. 14,904.
904.
And you'll have like
Right.
78 of one.
So, in theory, if there was a population that could double every single week, you bought 5 of them home. A month later, you're gonna have 14,000, right? So you might be here listening to your friend like, it's not a big deal. Okay, so whatever. I have 5 this week, it's just gonna be 10 the next week. It's not a big deal. Right? It can really affect how things are growing.
That's how
What
the
hap-
beetles in
what?
that's how the beetles in bio work. And as a cruel joke, they made like the kids count them on a weekly basis. And
Yeah, it grows really fast. It's exponential
they were
growth.
flying beetles that we had to count.
That's good. Yeah, it turns out that this is not dissimilar to how populations actually grow in reality. Of course, it's not going to be something as big as a 2, but you can always measure a population depending on knowing what its current size is, the proportion of the current size that it's growing per year, or every 10 years, or every 5 years. And so if you want to plan out where the population is going to be 50 years down the road, you can sort of make plans based on that. You can realize, well, we have to produce this amount of food, we have to produce that. You know, there's a lot of calculation that will go into this. So this is just one sort of example where, you know, people use this to plan things in the future. Yeah.
Can you just go over the relationship one more time again when you got to the equation?
This one?
The last equation you got to the box of y equals 5 and 2.
Oh, here I was given this information. This says when x is 0, my y is 5. So I went here, I plug in x equals 0, y equals 5. E to the 0 is 1. So that just becomes c. So I get c equals 5. Then I go back here, I know y is c e to the 2x. My c is 5, just put a 5 here. So this is describing the rate of growth of a population, for example, some theoretical population. This is actually describing the population at the current time, right? After X amount of days or weeks or whatever, this is how many I have, right? And you'd be surprised. Populations often grow this way because the thing is, the more people there are, the faster it will grow. It's not like linear growth, right? So 4 people make more babies than just 2 people, exponentially. When those 2 people make babies, now you have 8 people making babies. Then you have 16 people making babies. Then you have 32 people making babies, right? The number of babies is increasing. At first, it increased by 2. Then it increased by 4. Then it increased by 8. Then it increased by 16. And every unit time, it's actually increasing by more and more, right? So that's where all these things come in. So if you didn't realize how things would be crazy, can get crazy, this is the sort of thing that differential equations will help you understand. It's also, it's highly useful. It's one of those things that you can do a lot with. But that's just a basic idea of sort of why we care about differential equations.
You said that
So
y is the original value here?
Y is the current value.
No, over here. So the rate of change of your original number of animals,
Yeah.
right?
Mhm.
It's equals to 2 times the original.
2 times the current amount, right? I think of this y as a y of x. Y is a function of x, right? That gives me the current population, right? Y is the current population. The rate of change of the population is double whatever the current population is.
And
That's what I'm saying.
And that's something that would be given then.
Yeah,
I'm trying to figure out how you
describe.
apply this to like bacteria growth or something like that.
We will get there. It'll usually be a word problem. They'll tell you.
So this is the same equation as PE to the RT?
It's exactly the same kind of equation as PE to the RT. This is PE to the RT comes from this differential equation. I'm not sure if your professor in 205 actually derived that for you, but yeah. P naught e to the RT comes from this differential equation. It's the equation you get when you assume something grows in proportion to its current size, right? Which populations actually do that. And many other things actually do that. So this just goes to show, for example, that things can grow a lot faster than might be intuitive, right? And so people often ask things like, why do I need this math in real life? They might think that they're never going to need it, but you'd be surprised how useful just knowing the idea of what an exponential function can actually do would change, how it changes things, right? You open a retirement account and someone tries, oh yeah, 1% fee, right? You'd be surprised how that 1% fee happens, because they're going to be doing compound interest. It's not going to be growing like a straight line, it's going to be growing like an exponential, right? Over the next 40 years, they steal 2/3 of your retirement. You don't even realize it. If you understood exponential functions, you'd realize it. You would say, hell no, I'm not paying you 1%. Yeah, because it gets tricky. Things look small. Oh, it's just 5 hamsters. Right? Okay, I don't have to worry. It's just, I bought 5 hamsters. It's really not a big deal. Yeah, it can become a big deal. So this is just sort of explaining a hypothetical situation of how a differential equation can be useful. So it's just measuring, remember derivatives you can think of as rates of change, right? So this is just an equation that describes a rate of change. So to me as a scientist, we're taking measurements all the time, right? So yeah, I bought 5 hamsters home today. Okay, I have 5 hamsters. Come back into the lab next week to check how the hamsters are doing. There are 10 hamsters. What happened? Okay, maybe it was just a fluke. Come back the following week. There are 20 hamsters now. Okay, what's going on? Every week they double. What does that mean? Rate of change is double what it was the last time. What does that mean like 4 weeks from now? So let's keep going. So the thing is, we're not going to do any really complicated differential equations, even though the more complicated ones do show up in nature. We're going to do ones that are more like this, which they have a special name for it. So let me just mention that. There are many different kinds of differential equations. In fact, there's a whole class on differential equations here, which even in that class you barely scratch the surface. Engineering majors take it, like a whole semester where they just learn to solve different differential equations that show up in nature and in engineering. We will only care about simple ones. Called separable. We're going to be looking at first order. Don't worry too much about what that means. Basically, first order just means you're taking the first derivative. So I'm not really going to give you anything with a second derivative or third derivative. So separable first order differential equations. As the name suggests, separable means we can sort of separate things, right? Like we can separate the x's and y's. Put all the x's on one side, all the y's on the other side. In doing this, we can just integrate both sides to find the answer. Separated is with an A here, right?
Sure.
Or is it an E?
I think it's an E. I think it's an E.
I'm not an A. Whatever. I'm a math professor. I don't need to know this book. Siri's done. If Siri doesn't know, I'm fine with it. So basically what a separable differential equation is an equation that can be written in a certain form. This is an equation that can be written in the form f of y dy equals g of x dx, right? A few things to note here. There's a multiplication relationship. There's a function of y times dy. There's a function of x times dx, right? X's and y's are dummy variables. Sometimes I might use t for time or whatever. But once I can do this, get all the y's over here, all the x's over there, all variables on one side, all variables on the other side, where it's just a function times dy and a function times dx, this equation is called separable. The trick to doing these guys is to, of course, integrate both sides, right? In which case, chapter 1 comes in handy. That's what 1.2 is about. It's going to help us to solve differential equations, which, as I said, are pretty important. Because not everything grows in a linear fashion. Sometimes it grows as a percentage of itself. Like the more things there are, the faster it will grow. The less things there are, the slower it grows. What do I want to do? Okay, let's see if you can recognize when something is separable or not. Dy dx equals 2 x squared y plus 5yx. Dy dx equals 2x plus 5y. Dy dx equals y squared minus 1. Dy dx equals 2 minus x, or 5 plus y. Which of these are separable, which are not?
The first one is separable.
How do you know?
Because you can subtract 5y and then divide by y.
Can you
No,
factor
no,
out
you
y?
can't. No, you can't. Never mind. It's not.
Right, because that would, if I subtract a y, I'll get a separate term, right? I won't get.
Yeah, you can.
Yeah, you can. Can you factor
Factor
out
You
y?
can't.
I could factor out a y, I get x squared plus 5x,
And then divide by y.
and then divide by y. So I get 1 over y dy, multiplied by dx, I get x squared plus 5x dx. So yes, this one is actually separable. Remember the relationship, multiplication, which means if you're adding something to both sides, odds are you're making a mistake. You shouldn't be adding or subtracting. You should be multiplying or dividing to move things to the other side. If you can't figure out a way to do that, then it's probably not separable. This one.
Yeah, just minus 5y.
You can't subtract.
Oh, I knew. Sorry.
Just said that. Okay, so odds are if you want to add or subtract something to both sides, you're going to be wrong. You want to try to move things to the other side by multiplying or dividing. And if that doesn't work, odds are it's not separable. Okay, is this separable?
No.
No.
Right. The only way to move that y over here would be to subtract. Now you might think, maybe I could divide by y. This would be a problem, because then I'd get x over y on this side. I try to divide by y, I put a y in this term where it's not. Get rid of the y, they're multiplied by y, I put it back here. There's no way to get the x's and y's across with multiplication and division. So this is actually no, not separable. What about this one?
Not separable.
There's only one variable.
Good.
Sure. What if, can you do the square root?
Y plus root one.
No, no.
Can you square root?
I'm gonna go with no, because the answer is usually no.
What if you,
Don't worry, we'll do probability later. But yeah, the chances of me being right by discussing yeah, we'll deal with that later. Yes, it is separable. Now that I told you the answer, can you figure out why?
can you just do the integral?
It's gonna be like y minus 1, y plus 1.
Doing that wouldn't make any difference.
Just cross multiply.
Multiply
How
by
about I
5.
divide this whole thing under?
Why?
dy, divide both sides by y squared minus 1, multiply by x. Just take the whole guy and move them. Right? You don't have to think about moving one piece at a time. Sometimes you can just take the whole thing.
Because there's not.
So that is separable. What about this one? Cross multiply. I can multiply by this over there, and then multiply the dx over there. So this is also yes. In fact, that would look like 5 plus y times dy equals 2 minus x times dx, right? Which is exactly the form I need. It's separable.
No.
Wait. Yeah, no. It's not separable.
Have you been listening to anything I've been saying so far?
Wait.
Are you? What number are you with?
This one.
I feel like the answer is yes more than it has no, so I'm gonna go with yes.
So you go with probability again? You seriously think the answer is no? You look at this?
Yeah, you can.
He's throwing so much shade at you, it has no
If you
yes.
multiply by the reciprocal.
Please tell me you can do yes.
The answer is no.
Why?
I was like, you think so? It's gonna be an X.
The x and the y are mixed up. I can't separate an x or a y without affecting the denominator, right? So if I try to get the y out of this, I'm going to throw a y in the denominator, right? So that's going to be a problem.
I know to do it.
We're almost out of time. I'll just
No.
yes.
Then you can factor out x squared and then
Factor out x squared. What do I get? I factor out a y really. Well, either way, I would get x squared minus 1. Factor out a minus sign. I get an x squared minus 1.
and then y minus 1.
Factor by grouping ends up being y minus 1 times x squared minus 1.
Yeah.
Then I just divide by the y minus 1.
Just try to find
This means I have dy over y minus 1 is equal to. So we're doing differential equations in the class. This is half the battle, right? So I'm going to be giving you differential equations that are in a jumbled form. You first have to figure out how to separate the variables, and then you're going to solve it, right? So that's going to be the first step. There are going to be times where I'm going to describe in a word problem what's going on. You have to make up your own differential equation, then separate it to find the answer, right? So that's sort of where we're going. We didn't finish chapter 2, but chapter 1 is done, so homework for chapter 1 is due. We also have a quiz on Monday on everything up to here. I will see you guys there. And again, be sure to check that you actually need this class. I know if you're bio, probably economics, you need it. Psychology, BS, you can use it. If you're anything else, double check with your advisor. Okay, all right, see you later.